So that I've already told you. The exam is on Monday. In class, I don't know whether I'm still feeling a little under the weather, so I don't know whether I'll be able to proctor the exam or the TA will be there. I'm not sure. And the problem sets 1 and 2, the solutions are out there, and take a look at it. I think those give you the sort of problems that I'll ask, the type. So what I want to go today is that simply go through a review of condition control, right? Maybe a little bit of DNS, a little bit of DHT. The other things I don't think I'll be able to cover today. And we can also take a look at the midterm questions towards the end. So in condition control, what are all the important concepts? The important concepts that you are expected to know are the fundamentals of reliable transfer and ARQ protocols, right? So this stuff I covered in detail. I think I covered probably over a course of a week. Your textbook has even more material on state machines of reliability. So I would recommend that you look at the textbook, okay? Although usually I never ask things that I have not personally taught in the class for your own understanding, okay? So basically, let's see if I cover these things. No, okay. So the reliability, the basic idea behind ARQ protocols is that reliability is ensured by having an acknowledgement from the receiver that the previous segment has been received, right? So the dumbest plain vanilla form of ARQ protocols are the stop and wait, where you just send a piece of data, like a data segment, and then you don't even send the next data segment until you receive an ACK for that, right? So that the problem with stop and wait is that it wastes bandwidth, right? You have a wide fat pipe, but you're just sending a small amount of data and then you're waiting. So it's not an economical use of bandwidth. So then what do you do? In computer science, we know that when you want to get more job done, when we want to increase throughput, we always go for pipelining, right? So go backend basically adds pipelining to the basic type stop and wait. So instead of sending one, you keep sending multiple things in parallel until you can saturate the pipe. That's the idea, right? So basically, the difference between the two is one gives you much better bandwidth, the other doesn't. And the next thing that I expect you guys to know the difference between congestion control and flow control, like key difference. Like if you go to an interview right after you graduate, and then if you interview with a networking team in Microsoft or Google, it's very likely that this will be their first question in the interview that they'll ask you. Tell me the difference between flow control and congestion control. So what's the difference?
Congestion control is the actual traffic in the network. It depends upon how much flow the network is. Flow control is actually depends upon the buffer.
So the key word that I'm looking for is network versus receiver buffer. Okay, so congestion control is you want to make sure that you don't send more than the capacity that the network can support. So it's a function of the network. So for example, different networks may get congested at different times, right? Whereas flow control is really a memory issue. So whether the receiver has enough buffer to absorb the data that you're sending. Right, so that you should know, and you should also know, like in congestion control, the basic idea is that you increase when the network is free, and then you decrease when you detect that the network is getting busy, right? So there are many schemes on how do you do that increase and decrease. Of that, we sort of focused on this AAMD, right? And there's good reasons for that, right? What is the fundamental reason that AAMD is better than, let's say, additive increase, additive decrease? Why are if you look at all the transport protocols, congestion control protocols that we know today, they all do multiplicative decrease? Why is that the case? It's got to be more precise. Got to be more precise. Like, what is that AIAD would not give that AAMD gives? what is the unique advantage of AAMD? Fairness, right? So basically, when senders start sending at different times, unless you have a multiplicative component in the rate calculation, they won't converge to this fairness line. They won't converge to fair share, right? We had this figure with two lines, right? X plus y is equal to c and x is equal to y, and then you got to sort of, when there are two senders, they'll have to converge along that, the center line, x is equal to y. So that it's very intuitively easy to see that you cannot get there unless you have a multiplicative component, right? So that's one thing that you should know. And also the difference between basically we only discussed two important TCP variants: TCP Tahoe and TCP Reno, right? So Reno is strictly better than Tahoe, and what is the difference, and what optimizations that Reno does on top of Tahoe. You should know that, okay? So in TCP congestion control, the basic idea of TCP is easy, right? Every connection has a window, right? Window is nothing but the number of the bytes that are in flight, right? And by controlling the number of bytes that can be in flight, you're controlling the speed, you're controlling the sending rate, right? So the sending rate and window are directly related. So if you know an RTT of a connection, sending rate is simply the window divided by RTT. There is no easy way to control rate, right? That's why you control the window. Why is it hard to control rate?
Actual rate depends on
No, this is just a sending rate at the NIC, right? So it is possible to control rate, by the way. If you this simplifies a lot of implementation. If you want to really control the rate, then you'll have to add a rate limiter at your network interface. And instead of directly giving the window, you'll give the rate, and then you keep on pumping data into the buffer, and the rate limiter will limit that rate, right? So it's possible, but it requires rate limiters at the NICs, and if you don't want to put rate limiters, then the easiest way is to control the rate by controlling the window size. So basically, the idea is that you vary this window size to control the sending rate, and the way you do it is that you introduce this parameter called congestion window at the sender, and basically, congestion control is mainly a sender-side operation, right? It's mainly a sender-side operation. The receiver is not involved in this whole process, except, hacking, right? Giving you the acknowledgements. So two basic components. There is a component for detecting congestion, and there is a rate adjustment algorithm, right, which changes the congestion window size. It depends on whether there is congestion or not. So for detecting congestion, the basic idea of TCP Tahoe is that to detect congestion based on packet drops. There are other alternatives here, so you can also use the delay to vary the window size, and there are TCP variants like TCP Vegas which do that. We didn't discuss that, right? So just so you know that there are other ways to do it. So how do you detect packet drops? Basically, you keep on monitoring the ACKs. So the ACKs clock the sender, right? This is very important. Whenever you send the next piece of data, when you get an ACK for the previous, so ACKs serve as a clock at the sender. So also ACKs are cumulative, so they denote the contiguous. They denote the last contiguous stream of data that was received at the receiver. And actually, this is a minor detail. So the actual implementation, the ACK sequence number is not the last sent, but the next expected. So basically, two signs of packet drops. Basically, one is simple: if there is no ACK after a certain timeout, you ensure that the packet has been lost and you resend, right? It's a basic scheme. And the other method is to use any duplicate ACKs, because you know that ACKs always signify contiguous stream of data. When you have duplicate ACKs, it means that there's a gap, so you can do something about it. The data in between was lost or something happened, right? That was used in TCP Reno and other recent variants. So this may not work. This idea may not work well for wireless networks. Why? So we are using loss as a signal whether you use duplicate acts or whether you use timeout, you're basically inferring that any lost packet implies that the network is overloaded, the network is congested. Is that true in wireless networks? So in wireless networks, basically it's a shared medium, right? So that there could be collisions and there could be other signal issues. So the packet could be lost simply because there was noise, right? In which case, if you use this lost packet as a signal for loss, then you would. So if the loss is very random, not systematically created due to the load in the network, then this strategy will fail. So, and it fails. In wireless, it fails. So basically, we have not discussed it, but in wireless, the idea is that you use some link layer reliability. We'll talk about it when we go to link layer. So that TCP doesn't kick in. You fix it before even TCP cuts the window. That's how you fix it. So the basic structure of the algorithm, adjustment algorithm is that you increase the window whenever you receive the ACK, right? So the implication is that because the last sent data was received properly, you can probably push more. And then upon detection of loss, you decrease. So there are like basically two phases. There's a slow start and there's congestion avoidance. So initially you start from the initial congestion window value, which could be 1 MSS, which could be whatever. Okay, you can set it. It's a configurable parameter. And then there's also this threshold called the slow start threshold. So initially, starting from the initial congestion window, you sort of keep doubling the congestion window until you hit there's a threshold after which you additively increase by 1. And meanwhile, when there's loss, you will back off. Right, that's the idea. So initially, it's an exponential curve, right? Right. Initially, it's an exponent. You're doubling it, and then it's linear, right? And then there could be when there is drops, then you will again back off and start over again. So basically, this is the illustration, right? So initially, when you're starting, the sender starts with 1 MSS. On receiving the ACK, it increases by 2 and sends 2 data segments. And then as it receives the ACK for both of them, it increases to 4 and so on, right? So basically each ACK generates 2 packets, and during slow start, the rate increases exponentially fast, right? It's double every RTT. So why is there slow start? No. What if you don't have slow start? So basically, you'll ramp up really slow. So if you have an infinitely long file, it doesn't matter. But in real life, nothing is infinite, right? So basically, you're dealing with finite objects. So you'd want to send that object as quickly as possible. So if you don't initially ramp up, you will waste a lot of time, converging to that point. So basically, slow start is sort of this SS threshold gives you an idea of what a safe limit could be. So because you know that SS threshold is a safe window that will not overload the network, you can sort of rush to that point very quickly. But what is important is that whenever you have a loss, right, whenever you have a timeout, you have the slow start threshold, because you rushed too quickly. Right, so you set the slow start threshold as half of the current congestion window. So this is the same figure showing the time on x-axis and congestion window on y-axis. Here it assumes that SS threshold is 8, right? So basically, starting from t is equal to 1, you just go 1, 2, 4, 8 really fast, right? And then after you hit 8, you just increase it linearly by 1, 9, 10, 11, and stuff like that, right? So if I ask you, what is the bandwidth, right, that this connection obtained in this figure, what will it be? Like if I give you this figure, right, and I ask you, hey, tell me that, I had a connection, it lasted for how many? Oh man, I can't read it. So maybe 8, I think. Lasted for 8. Maybe 9. Right? It lasted for 9 seconds, right? So basically, I told you, hey, I had this connection. This is how the connection window looked like, and it lasted for 9 seconds, right? Um, 9 seconds or 9, whatever the x-axis unit is, right? If I ask you what is the bandwidth, how do you calculate that? Huh? Sum up? No, I gave you that figure, right? What is the bandwidth? Huh? Yeah.
Area under the curve divided by 9.
Correct. Correct. It's the bandwidth. So the area under the curve is telling you how much data you have sent so far, right? And 9 is the time that you took to send the data. So the bandwidth is simply the area under the curve. And this is very nice, right? This is a geometric series, right? So if you know geometric progression, right, from high school, you know how to sum up a geometric progression, and you know how to sum up the arithmetic progression after that, because one is linear, one is geometric, and you can just sort of derive actually a nice closed form equation if you want to. So the one phase that I didn't explain is the multiplicative decrease. That is, on condition, you decrease the window. So every time the condition occurs, you set the slow start threshold to half of the current condition window, not the previous SS threshold, right? And why do you do that? Because when you hit condition, the current window was too much. So you want to go back one step, but you don't want to stay there, because but maybe the condition is an intermittent event. It will become better after. So you want to go back and fine tune slowly. So you sort of roll back the SS threshold to congestion window divided by 2, right? And then from that point onwards, you start congestion avoidance, basically, because you're finally adjusting. So basically, you finally adjust, or you go back all the way from 1 and start, depending on whether the congestion is a timeout or a duplicate ACK. Right? So basically, this is also another thing. If I give you this figure and I ask you what is happening at what part of the figure, you can easily tell it, right? Obviously, the exponential growth is slow start, right? And you can also know that slow start threshold from the inflection points of the curve, right? So, for example, like all these points where the curve changes from geometric to linear, that's all slow start threshold. And then timeout is obviously, you'll have a long flat line because you're not receiving anything, right? You're not sending, you're not receiving, you're just waiting. So, yeah, it did not come to 0. It's actually, the y-axis is actually starting at 1. So it came to initial condition window. It's not 0. Right, and you should be able to tell the different phases, right? So the basic algorithm is TCP Tahoe. We discussed it, and Reno is basically adding fast retransmit and fast recovery to Tahoe. So it's a very incremental fix over Tahoe. So most end hosts today use what is called as TCP new Reno. So I think Linux uses TCP cubic, I think, but I think some versions of Linux use TCP new Reno. But basically, this Reno forms the basis for all modern TCP protocols. Yeah.
So, previous picture. So, once you reach a threshold, instead of going exponentially, you go linearly?
Correct. Yeah, because the threshold is telling you, hey, you no longer can be wild beyond this point, right? So you got to be finely tuning it.
Are we going to take the derivative then? With respect to x? That's it, find the area of the term?
Sorry?
Uh,
No, I think, sure, yeah, I think, if you want to find the area of the curve, that's what, you'll not take the derivative, you'll integrate the line. You'll integrate, right? You want to do area. It's not derivative. You'll have to integrate this curve, right, over the x range. Yeah. But anyway, I'm not going to sort of ask you to do calculus, right? I mean, usually it'll be simple. You can sort of manually do it. That's not the point, but it's sort of an intellectually curious thing to think about it this way. So, what else? And there are also other more, like the TCP Vegas, the one uses timing of the ACK. TCP SAC uses selective acknowledgements. Not important, not covered. Okay. So, what is the problem with TCP Tahoe? That is, if your segment is lost, there's a long wait, right? So you are not really, you're just wasting. So, what Reno does is that it adds a fast retransmit and a fast recovery mechanism. So, fast retransmit is basically upon receiving 3 duplicate ACKs, you retransmit the presumed lost segment. And fast recovery is that basically you don't set the congestion window all the way back to the initial value, but you just go one step back and start congestion avoidance from there. So basically you set the congestion windows is equal to congestion window divided by 2, and you set slow start threshold at that point, which means that you're already in congestion avoidance. Then you sort of fine tune. So the same thing shown pictorially, right? So in this case, you send 1, send 2, and then let's say the third round, your first segment was lost, segment 4 was lost, and then after you get the 3 duplicate ACKs, you can start. You don't have to wait for the timeout. The thing to note down is that remember that when you get a duplicate ACK, it means that the receiver received something. It's just not the next in line, but it received something. So which means the network is not totally broken. It's very different from timeout. That's the reason why you are also not going all the way back to 1. You're able to sort of step back and fix it incrementally. Another thing is that this duplicate ACK business, right, doesn't work if the window is already small, right? For example, if segment 2 had been lost, right, then you would not have received the duplicate ACKs, right? So because your window is already small, it's smaller than 3. You don't have 3 outstanding data segments that are pending after the last segment, lost segment. So what this also means is that this is okay because if the window is that small, then perhaps even going back to 1 is not so bad, right? The incremental advantage of fast retransmit and fast recovery is not there. The window is small. That's why it's okay. Also, duplicate ACKs might also happen if the network reorders. It's another thing you'll have to keep in mind. For example, this is assuming. So, what am I assuming? That if I am able to detect congestion using duplicate ACKs, what is the central assumption here about the order of packets that the network will deliver to the receiver? Correct. So I'm assuming the network is delivering the packets in order, right? Which means I'm automatically assuming that my routing algorithm is such that all the packets belonging to a flow are delivered in the same path, right? Sequentially. So if you're using, which we have not covered it, but if you're using any funky routing algorithms, they can split the flow and then spray the packets across, and then all the packets will reach the receiver in their own order, and all of this will be off, which means that you'll have to turn off this optimization. So in modern data centers, which is often the case, so you go and turn off the optimizations, and you'll have to turn off. Basically, you'll have to turn off for fast retransmit and fast recovery, because by design it's supposed to be reordered. So we talked about this, right? After fast retransmit, set the congestion window equal to congestion window by 2. SS threshold is equal to congestion window. Those statements are sequential, okay? You cannot swap the order of those statements. It will not make sense. And then you start the congestion avoidance at the new congestion window. After a timeout, it's say the SS threshold is made congestion window by 2, similar to before, but then you reset the congestion window. Then you enter slow start. Any questions? on this. So basically, understanding this how this window control works on a network, this is important. Okay, I think you should that you should be very clear in your mind. Any questions?
Sorry, can you just repeat that last thing you said?
Which part? Sorry.
One more time.
Which part?
Very last sentence. One last sentence.
Very last time.
All this should be very clear in your head. One more time.
Oh, I was saying that I think the way the congestion control works in TCP, the different pieces of it, like there are different pieces here, right? There is slow start, there is congestion avoidance, there is fast retransmit, there is fast recovery, right? You should clearly understand this. What mechanism is for what purpose, and what does it do and what does it not do, and what are the limitations of these. For example, fast retransmit, fast recovery cannot be applicable if the network is going to reorder the packets. So the other thing of the other aspects of the class that you should focus on, I think you should understand the whole DNS hierarchy. So why DNS is done the way it is done today? That is basically, why do you have this? Why do you do the resolution hierarchically, starting from the root level and top level domain servers, and then the local servers, right? So you should understand why it's done that way, and basically the hierarchy itself, right? If I'm asking you to say, hey, how will this DNS querying work? You should know that you have to walk through the hierarchy, right? And also the advantage of it, right? The hierarchy is what that makes the whole scheme scale to billions, right? Tens of billions, hundreds of billions of web pages, and there are also the hierarchical nature of the DNS names sort of helps you. These are very common tricks, right? Hierarchy and indirection. Simple stuff. And basically, actually, if I give you an example, right, how this DNS resolution will work, and if I tell you I'm using iterative queries versus recursive queries, you should be able to tell me the steps. For example, in this case, the first time the requester goes to the local DNS server locally, it's not there, so it goes to the DNS root. The root actually returns an NS record, right? Because it doesn't have the translation, but it knows the next level. So it'll return the NS record, right? And then you'll again go to the top level domain server, and then blah blah blah. You'll repeat, and then finally you'll finally get the result. In recursive, the burden is on every server. So as soon as you ask the root server, the root server will actually ask the next guy and the next guy, and then it's the entire whole shebang. So, and also if I ask the general idea of if you want to sort of create a new network domain, right? So what are the steps you'll have to do? So the first thing is that you'll have to first register your name at a DNS registrar, right? Let's say I want to have a new startup. First step is to register in the registrar, and I have to provide him with the names and IP addresses of the authoritative server. That's what he needs to know, right? And then the registrar will insert the DNS records. In this case, 2 records, right? One is the NS telling you who is the authoritative server, and then the other one is the actual translation for the server, right? And then at the local level in your authoritative server, you want to add a record and an MX record for the local resolution to work. So this you should know. Another thing I am really interested is also that you should know how the distributed hash table works, right? Not simple stuff like simple query semantics, but rather not these things, right? So basically, this one, right? So basically, in the distributed, in the consistent hashing, you sort of assign the key value pair to the peer that has the closest ID, right? This closest is key, right? and closest is actually the immediate successor of the key. So basically, if I tell you that my ID space is 0 to 64 by 6 bits, and then I have 8 peers with some IDs, and if I tell you that this key is 51, you can tell that it's assigned to the peer 60. It's always the next highest one, right? The closest immediate successor, right? So basically, the fundamental idea behind consistent hashing. So what is the idea of, why is consistent hashing great? What is the single beautiful thing about consistent hashing? Like the idea of assigning to the immediate successor. What does it give us? I mean, obviously, this is the only way to do it because that particular peer may not exist, right? That's why you're putting it to the successor. But there is a nice added benefit to this strategy. The benefit is if a peer leaves, right, only that peer's key will just move to the guy next, right? You are not reshuffling the entire thing. For example, in regular hash tables, let's say you are hashing based on mod 8, okay? Typical way to using mod is the dumbest but easy, the most straightforward hashing that we know, right? If you do it, and let's say when I do mod 8, what I'm saying is that I have 8 bins, right? 8 buckets. Now let's say one of the bucket is gone. Now I have 7. Now if you do mod 7, you have to rehash all your existing items. You have to go to the bucket. You have to go to all the items in all the buckets, and you have to redistribute. In consistent hashing, that's not the case. If one of the bucket goes away, one of the peer dies, just have to move those subset of keys. That's nice, and that's sort of it's a marriage made in heaven because P2P systems often are not reliable. They'll go down, whatever happens. So this works beautifully. And the other thing is basically in HTTP, you should know the HTTP support for cookies as well as the proxy servers, right? Browser caches, HTTP caching. So, yeah? Sorry? Which one? Yeah. I mean, the caching is implemented using the DNS support, right? We discussed when we discussed the CDNs. So basically, the DNS server, instead of redirecting you to the actual domain, will redirect you to a nearby proxy server. But also, HTTP has to provide that support, right, for caching, that if used or something, so that you know that the item is stale or not. The cookie thing is simple, right? Cookies help you add state to otherwise stateless protocol, right? At a high level, that's what they do. And the way they do it is that you sort of exchange some sort of ID initially when the first time you're handshaking, and from that point onwards, you can sort of maintain all the state at the application layer in the server, and you can sort of access that state using this cookie ID. That's a very high level idea, right? So that you should know. So that's all I have on general review. Any questions? Any areas that you want me to discuss? Any questions? So the one problem, if you guys don't have much idea, then one thing I wanted to talk about is this one. Okay. Is there a way I can do this slideshow? It's the same thing. Doesn't help. Okay. What happened? Okay. I think a better way is to do it like this, because then I can control my zoom. Hmm? Sorry?
Where are these again?
These are in Piazza.
Yeah.
Yeah. So these are some of the example problems that I had, right? So this is easy, right? This is dummy problem. This is super easy, correct? So basically the question is that you want to design a reliable That's what layer protocol, and your network uses some speed link with some RTT. If you use stop and wait, what is the maximum achievable bandwidth? That's straightforward, right? What is that? It's basically in stop and wait, you're only sending one MSS, right? So basically, it's one MSS divided by RTT. That's the bandwidth that you'll achieve, right? And if you're using this go back N, then you will achieve close to 100 Mbps. That's the goal. So you will set the N such that you will get 100 Mbps. So if I ask you what is the N such that it achieves the maximum bandwidth, it's basically N times 8 KB because each segment is 8 KB divided by RTT, right? Which is 10 ms. That should give you 100 Mbps. So yeah. So I'm treating as 1024. So basically, this is how you should treat, okay? If something is mentioned in bytes, right? If I say kilobytes, and if you're converting to bits, it's basically 1024 multiplied by 8 bits, right? But in Mbps, right, that M and K in bandwidth, that is always 10 power 3. So as you go from this binary metric, right, which is bytes, kilobytes, and all that, each factor is 1024, not 1000. But if you are in the bits, if you are in the bandwidth numbers you're talking about, when I say 1 gigabits per second, it's 10 power 9 bits. That's it. But that's not important. I'm not going to cut. I don't. That's not important. That's not the point of testing, right? So this is all easy. The other interesting problem is this problem that is there. That is, if you have a network like this, right? Two computers are there, and that's some speed, 1 gigabits per second in this case. There's a 1 Gbps switch, so everything is good. And let's say you have the network round trip is 200 microseconds, and the maximum segment size is 536 bytes, which is very common, right, today's networks. And there is some initial condition window, which is 10 segments, and slow start threshold is something, in this case 10 segments. The question is, basically the question is, if you want to saturate the link, what should be the condition window size? It's the same as the previous question, right? Your size should be such that the bandwidth is 1 gigabits per second. So basically, window divided by RTT should be 1 gigabits per second, and then you can calculate. It's very easy, right? It's not difficult. Basically, if you calculate, it's around 47 segments. The interesting question is the second part, which is if I ask you after how many rounds, right? In this case, how many round trips? Rounds is equal to round trips. After how many round trips will the average sending rate, right? That is the total data sent divided by number of rounds multiplied by RTT. Reach 90% of the link bandwidth. Then you basically then you'll have to know how TCP works. This is a type of problem that sort of allows you to apply all the concepts together. So basically, if you from the slow start threshold, right, and the initial congestion window, right, both are 10 MSS, which means there is no slow start. You will start with congestion avoidance, right? And then you are going to manually increase. So, in the first round, it will be 10 MSS, right? In the second round, it will be 11. The third round, it will be 12. And then it will go on for some time. You don't know how many. That's the question. So, up to some n terms and divided by n RTT. That's the interval. That should be greater than 0.9, 90% of 1 gigabits per second. 0.9 of 1 gigabits per second, right? And, you'll have to solve for n. And this is where, if you know that this is basically an arithmetic series, arithmetic progression, then you can do some math. But even if you don't, you should be able to calculate this manually, right? So this problem is easier in this case because there is no slow start. If there is slow start, this numerator, right, you'll have to split it up into two parts. One will be the slow start part, which will be geometric progression, and one will be a congestion avoidance part, which will be an arithmetic progression, and then you'll have to solve for n. Right, but obviously in this case, these type of problems, I'm not expecting you to do complex arithmetic, but I'm expecting you to write that expression to know that you understand. So I think these kind of problems, right, you should expect. You should not get tripped up. And here I've also made one simplifying assumption, right? Let me tell you who can catch that. In this calculation, I've made one simplified assumption. Good catch. So basically, I've assumed that RTT is not increasing, right? But in real networks, as you pump more and more data, it will initially the queue will be empty, right? So your RTT will remain constant for some time. But after some time, the queue will start building up. So there's an extra queuing delay that starts coming in, right? So your denominator will not be a simple n times RTT. It'll be more than that because time is also expanding. This makes it complicated. And usually the queuing effects are nonlinear, which means that there's no easy way to model that. That's the reason that if a student were to come to my office and argue and say, hey, you did not mention it, I'll have to begrudgingly give him the score because he's right. So basically, I'll have to qualify this question by saying, assume that the RTT is constant for simplicity. Good. I would gladly cover a little bit of queuing theory if there is time in the end. It's very interesting to study how this RTT will change as you pump more and more data. So all other questions, right, are pretty straightforward. The one I think we also covered security towards the end of the application layer, so that's also included. Okay, but most of the questions in security will be short questions, right? Just those are all easy pickings. Okay. So that's all I have. You guys have any specific questions? Yeah. Sorry? You mean papers? So I think the only paper where there might be so basically the papers that I have covered in the class you could expect, which so happens that there's only one paper that I actually covered. All other things are basically readings or fluff. Like end-to-end argument is a nice thing, but it's not really deep, right? But DC-TCP I covered, right? So you can expect, stuff related to DC-TCP. But for example, the CORD paper, which is also one of the readings, we didn't go into the gory details of CORD, right? I just told you how this DHT consistent hashing works. How do you what happens if a node dies? What happens if a node joins? But that's about it. I didn't go into the whole log and lookup kind of thing. So those things I won't. So I think good rule of thumb is whatever I have spent a substantial amount of time discussing, substantial meaning at least one class worth of time, I will, you can expect. Okay, all right. I think that's all I have for today. Good luck, and I think if you come to the class and if you've done the labs, it shouldn't be hard.